Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and we're here today to get ready for the AP Chemistry exam in May. In this webcast, we're going through free response question number 3 from the 2022 exam. This is one of the long free response questions, and that means it was scored out of 10 points. Another thing to note about the long free response questions, they're going to have multiple parts, 7, 8, even 9 parts to the question, and they're going to jump from one topic to another, so you need to be ready to shift gears as you work through the problem. Go get your calculator and your periodic table and your formula sheet. What I want you to do is listen to me introduce the problem and then pause the webcast, try to answer it on your own, and then listen to my explanation so you can score your own work as you go. Did you earn the point? Did you not earn the point? What do you need to do to enhance your answers to get full credit so you can show off all your chemistry knowledge that you worked so hard this year to learn? Let's jump right into the problem. Answer the following questions relating to the element aluminum. Part A, write the complete ground state electron configuration of an aluminum atom. So if we look at our periodic table, an aluminum has an atomic number of 13, and that tells us that a neutral aluminum atom has 13 electrons. Based on the position in the periodic table, we see that we're in period 3, and that tells us that the highest occupied energy level for the outermost electrons of aluminum is energy level 3. And it's in the P block. Specifically, it's in the first column of the P block. And that tells us that the last electron of the electron configuration will end as 3p1. So now we're ready to write the electron configuration. Alphabet principle, we always start with energy level 1, 1s2, 2s2, 2p6, 3s2, 3p1. That's our complete ground state electron configuration. Now, the noble gas notation was also accepted for full credit. So you can write the symbol for neon in square brackets representing the first 10 electrons, and then we write the remaining valence electrons, which are 3s2, 3p1. So either one of these formats were fine. If you wanted to write arrows in boxes, that was okay too. This was what you needed to write down to earn the point for Part A. Part B, based on principles of atomic structure, explain why the radius of the aluminum atom is larger than the radius of the aluminum ion. Now, the aluminum ion has formed because we've lost 3 electrons, and that's going to be important. The other thing I really want you to note here is look at the question. It says, based on principles of atomic structure. This is a big clue that your answer needs to discuss either occupied energy levels and or nuclear charge Coulombic attractions in your answer. If you want to get full credit, pay attention to these clues. So we know that a neutral aluminum atom, of course, has the electron configuration we wrote in Part A. The aluminum ion has lost 3 electrons, so it's lost the 3s electrons and the electron in the 3p sublevel. So we're left with 1s2, 2s2, 2p6, which is isoelectronic with neon. The outermost electron in a neutral aluminum atom is in energy level 3. That's our highest occupied energy level. Whereas in the aluminum ion, the highest occupied energy level is energy level 2. And that's really the core of what our answer needs to address. The outermost electron in a neutral aluminum atom is in energy level 3, which is farther from the nucleus than the outermost electrons in the aluminum ion, which are in energy level 2. That is really what your answer needs to focus on. You don't have to write out the electron configuration for the aluminum ion. Heck, you don't even have to write complete sentences. Bullet points are great, but this is what your answer really needs to address. And that's what you needed to talk about to earn the 1 point for Part B. A student plans to combine solid aluminum with an aqueous solution of silver ions. The student determines the mass of solid silver nitrate needed to prepare the solution with a specific concentration. In the following table, which I haven't shown you yet on this screen, briefly list the steps necessary to prepare 200.0 milliliters of an aqueous solution of silver nitrate using only equipment selected from the choices given. Assume that all appropriate safety measures are already in place. Not all equipment or lines in the table may be needed. So what do we have here? We've got solid silver nitrate, distilled water, a balance, weighing paper and a scoop. We have a 200.00 milliliter volumetric flask. We have a 50.0 mil graduated cylinder. We have 250 mil beakers, and we have a pipette. What glassware do we need to use? Note that we're trying to prepare 200.0 milliliters of this solution. We want to know this volume quite precisely. And the glassware we have available is a graduated cylinder, a volumetric flask, and a beaker. The graduated cylinder is nice. It might be marked to 1 mil, which would give us adequate precision here, but it's only 50 mils, so we can't prepare the solution in that. Plus, it's a bad idea to prepare solutions in a graduated cylinder anyway. The volumetric flask, however, is marked 200.00 milliliters. It can only do that one measurement, but it can do it really, really precisely, and that's really the best choice. Beakers are not a good choice here. You can't have any confidence in that volume measurement. It's going to be off by at least 5%, maybe more. So to prepare this solution with a total volume of 200.00 milliliters, with the available glassware, a volumetric flask is hands down the best choice. We need to make sure that that's mentioned specifically in our answer to Part C. So step 1 is given to us. We're going to use weighing paper to measure the determined mass of the solid silver nitrate using a balance. What do we do next? We know we're going to use a volumetric flask, so I've got that illustrated here. In fact, I've got a clue to step 2 in my drawing. The next step is to put some distilled water into the volumetric flask, but we don't want to fill the volumetric flask all the way. We want to have some room in there to continue filling it later. And then we're going to transfer the mass solid into the volumetric flask. Remember, it's the total volume of the solution that we need to be 200.00 milliliters, so we don't want to fill it up all the way. We want to put the solid into the flask and actually mix it. So I recommend that you put the stopper in the flask and invert it several times. That's good laboratory practice. And then once it's been mixed, then we'll finish filling the volumetric flask with distilled water until the bottom of the meniscus is on that 200.00 milliliter line. And that is the key thing that you need to address in your answer here. Personally, I think you should mix the contents again, but we've hit the key points here. This question was scored out of 2 points, and you needed to hit both of them. You needed to make sure that you mentioned dissolving the solid in water, and you needed to mention that you're going to bring the total volume up to the calibration line of the volumetric flask. And if you didn't mention using volumetric glassware here, you weren't going to get full credit. After preparing the solution, the student places some of the solution into a beaker and adds a sample of aluminum. The reaction represented by the following equation occurs. So we have solid aluminum reacting with silver ions in a 1:3 ratio to form aluminum ions and silver metal. We've got a particle level model in the beaker here. Now this beaker is showing us what we have before the reaction has occurred, but after we've combined the materials. My advice here, anytime you see a particle level model, always count your particles. It's going to become very useful. So the initial conditions here are that we have 4 aluminum atoms present in the mixture and 8 silver ions. The other thing I want to point out, we've got starting amounts of both reactants. Is this going to be a limiting reagent problem? Okay, let's go on. The following diagram gives an incomplete particulate representation of the reaction. The beaker on the left represents the system before the mixture reacts. Complete the drawing on the right to represent the system after the reaction has occurred. Be sure to include 1, the correct type and number of particles based on the numbers shown on the left, and the relative spacing to depict the appropriate phases. We started with 4 aluminum atoms originally. Now only 2 aluminum atoms remain. That tells us that 2 aluminum atoms reacted to make aluminum ions. So we can think about that when we go to draw our particle level diagram. Now looking at the stoichiometry of the reaction, for every aluminum atom that reacts, 3 silver ions react. Since 2 aluminum atoms reacted, that tells us that 6 silver ions reacted to form silver metal, and there must be 2 silver ions remaining in solution because they're in excess. So yeah, this is a limiting reagent problem. I'm going to have those 2 silver ions remaining in solution, and I'm going to deposit 6 silver atoms on the bottom together as a solid. And I'm going to make 2 aluminum ions also in solution. And this is what I should have in my representation of the beaker on the right for after the reaction. How was this question scored? It was scored out of a total of 3 points. To earn the first point, you needed to show conservation of mass. We had 4 aluminum atoms originally, and now I have 4 aluminum species present. 2 aluminum atoms, 2 aluminum ions. I started with 8 silver ions in solution. I still need to have 8 atoms or ions of silver in my solution, and I do. For the second point, I needed to show that what was left in solution correctly. I'm going to have 2 aluminum ions in solution and 2 silver ions remaining. And for my third point, I needed to show states of matter appropriately. I needed to show those 6 silver atoms together, clumped together as a solid. I got them as close together as I could. And that I have 2 aluminum ions in solution far away from each other. And that's what needed to be shown here to earn all 3 points for this problem, which really had a lot going on. The student finds the standard reduction potentials given in the table, which are related to the reaction that occurs. Part E says, using the standard reduction potentials, calculate the value of E0 for the reaction. We know that the silver ions get reduced. We know that aluminum atoms get oxidized. But just working from the standard reduction potentials, the silver half reaction has the higher E0 value. So we're going to keep it as written, which is consistent with the reaction we already know happens. The aluminum half reaction has the lower value for the E0 value. So it's got to be flipped around. So we're going to keep the 0.80. We're going to flip the 1.66 and change its sign. And we're going to add everything up. So E0 for the reaction is 2.46 volts, which is a positive number. Now that makes sense. We know that when we put the aluminum metal into the silver nitrate solution, that this reaction occurred. And so having a positive value for E0 here is consistent with that. That's what you needed to write down to earn the 1 point. I do want to remind you that you needed to show your setup for the calculation. Don't just have an answer appearing out of nowhere. Write down the math that supports your answer. Otherwise, you're just not getting the point. We don't want that to happen. Part F. Based on the value of E0, would the standard free energy change of the reaction under standard conditions, delta G naught, be positive, negative, or zero? Justify your answer. Well, we know that the value of E0 is greater than 0. We know that the reaction occurs spontaneously. These two statements are really saying the same thing in different ways. Delta G is defined as negative NF E cell, where N is the number of electrons transferred, F is the Faraday, and E cell is the overall cell potential. Since E cell is positive, delta G is negative. The fact that the reaction occurs spontaneously fits right in. I do want to remind you that when you see the phrase justify your answer, it means use math-based reasoning or refer to data in your answer. And that's what we did here. And that's what we needed to write to earn 1 point for Part F. Part G. Once the reaction appears to stop progressing, would the change in free energy be positive, negative, or zero? Justify your answer. There's actually 2 ways we could answer this question. When the reaction appears to stop progressing, E cell would be equal to 0. If E cell is 0, delta G is 0. And that would be an adequate answer right there. Alternatively, you could have said the wording suggests that the reaction establishes an equilibrium. And if we're at equilibrium, delta G is equal to 0. Either one of these is fine. It was worth 1 point for Part G. How did you do? In 2022, the average score on this question was 4.59 out of 10 points total. A fairly high scoring question. So if you earned 5 points or higher, you're just fine. You're in good shape. If you earned 7 points or higher, kudos to you. If you found this webcast to be helpful, like the video and leave a comment. And remember to subscribe to my channel so you get all my latest updates, all my review materials, and you're ready to go for that AP Chemistry exam. Remember, it's always a good day to study AP Chemistry.